Okay, so what we're going to be doing now is we're going to be working on a related area where we're going to again be looking at integration and this whole idea of accumulating, but we're going to look at accumulation from a kind of a different perspective. Okay, so in previous incarnations, when we were accumulating, sometimes we would go through and we'd accumulate points. Okay, and that accumulation of all those points that ended up giving us the length of a line that ended up giving me an arc length. Okay. On the other hand, sometimes what I would end up doing is I would end up accumulating arc lengths, right? So I'd end up adding up arc lengths to like these figures, and when I accumulated all of those together, I get the surface area for a solid, okay? And so if you look at that, you can kind of think, okay, well, points, they're one-dimensional, okay? So I've got points points are zero-dimensional. And when I integrate them, what I get, so the integration of points, that ends up giving me something, I end up getting arc length, and that is one-dimensional. Or, say for example, so here's like example 1. Example 2, we've seen now, is we have a function, all right? And a function ends up being one-dimensional because it's like a line or it's a curve in space. And when I integrate, okay, my integration ends up giving me an area, and that area is two-dimensional. Same thing when I have example 3 and I take an arc length. When we were working with surface area, that again is one-dimensional. And when I go in and I integrate, what I get is I get a surface area, and that surface area is two-dimensional. Okay? Now what we're going to be doing now is we're actually going to be taking the same basic idea of utilizing integration and accumulating pieces together in order to generate volumes. Okay? So we're going to look at now our next example here as we work more and more with integration. Our result is going to be, we want to get a volume, and a volume is three-dimensional. And so if you kind of look at the relationship we have here, that every time I integrate, I go up a dimension. Right? I add an additional dimension each and every time. I go from one-dimensional to two-dimensional. Now I need to go to three-dimensional because I want to find a volume. So what I'm going to do is I'm going to take a two-dimensional surface and I'm going to integrate it. Right? And that is an area. So I'm going to take an area, all right, and I'm going to integrate the area, and what that's going to do is that's going to allow me to generate a three-dimensional surface. So what we're going to do is we're going to imagine that what we have is we have a surface, right, and it has a cross-section of some sort. And that cross-section, the most common one we're going to use is like circles, all right? So like let's say, for example, we imagine my coffee mug, okay? We imagine my coffee mug, and if you kind of imagine my coffee mug, and we're going to try and find the volume of it. And it's kind of got it's a strange looking kind of surface. It's got kind of like a curve coming through here, all right? But if I kind of turn it on its side, what I'm going to see is I'm going to see that my cross-section here, this cross-sectional value is a circle, all right? So that's the basic shape of my coffee mug. It's essentially a cylinder, all right? And so we're going to utilize that idea in order to generate volumes for kind of stranger surfaces or surfaces like my coffee cup, okay? So let's imagine just a very basic way of thinking about my coffee mug, okay? And let's imagine that my coffee mug is just a very basic cylinder, all right? A basic cylinder. Because essentially that's what my coffee mug is, and this is going to be kind of easy to deal with. I know that my volume, the volume of my cylinder, is going to end up being pi r squared times h. That's actually the volume of a cylinder. But what if now, and that's because r is constant. All right, r is constant, and then we have this h value. And kind of what I want to imagine with the h value is that I've got this line going through here, and that's an axis. All right, let's imagine, just for the sake of argument, that this is basically our x-axis, okay? But r is constant, so it's a pretty easy way to kind of imagine finding that volume of the cylinder. Just know what R is, know what H is, and we're all good. Let's kind of see if we can generalize this, though, to thinking about integration. Okay, well, what I want to do is I want to say, okay, so I'm going to turn my coffee mug on its side. Okay, and essentially, what I'm going to see here is that when I turn my coffee mug on its side, one, you're going to notice that surface of revolution that we've talked about before. Okay, and I'm going to have this. Here's my radius. Okay, and here's some kind of x value. All right, and what I'm going to do is I'm going to take pieces. All right, I'm going to take pieces here, like little mini volumes, so that each one of here is a delta x. Okay, so there's delta x. All right, so the value of each one of these ones here is that delta x value. And so that's my interval. And as before, we're going to assume that each one is exactly the same. So if I kind of break up my cylinder, my coffee cup, into pieces, what I'm going to see is I'm going to get a bunch of these cylinders, and I'm going to add up, basically I'm going to add up their volumes. So my V, my volume, we'll call it V star, okay, is going to equal a sum. And this sum, well, it's going to have that delta x on the end of it, as we've seen before, because that's going to end up being my height. And I'm going to have a pi, and you might notice that this r, okay, that r, it tends to be the same in this case, but we could even imagine it kind of changing, and let's just say that that's going to be an f of xi star, okay, right? It's going to be basically, in different cases, we're going to imagine it as being like the midpoint between the midpoint of any one interval, you know. It could be a lot of things, but let's just have it be a f of xi star, and that's essentially, that's going to be my radius. So that's going to be my radius squared. Okay? So I've got pi times my radius squared times delta x. Okay? And I'm going to go I equals 1 up to n for however many that I have. Now, I'm going to find v. I'm going to take the limit as n approaches infinity for v star. And that'll equal the limit as n approaches infinity, okay, of the sum I equals 1 up to n of pi times f of xi star squared times delta x. Okay, so basically what I've done is I've gone in here, and this is my area, and we sometimes we're going to call this a of xi, okay, star. All right, and then we multiply that by each delta x. And so that's an equivalent way of writing this particular formula. Well, what you're going to notice is that this, and by the way, this is still the limit, as n goes to infinity, okay, this is going to end up being my integral. So it's going to be the integral, and we call this the integral of a of x, okay, dx. And this will go from some x naught to x1 if we're, what we say, revolving around the x-axis. So this ends up being my volume. My volume is basically the area of any cross-section, okay, integrated across some kind of interval. And so the trick is going to be, for this particular one, is to figure out how do we find those areas of the cross-section? How do we visualize them? And basically what we're going to do is we're going to think about, you know, what the figure looks like and work from there. Okay? All right, so let's take an example, right? We saw this example right here, all right, of our cylinder. Let's say, for example, I'm looking at a cone. All right, so I've got a cone. And the cone, we know, is 7 centimeters high. All right, and the radius of the cone is always equal to the height of the cone at all heights from 0 to 7. So if I imagine what my cone looks like, here's my cone. There's my cone. In this case, here's my height. That's 7 centimeters. And then actually at the bottom, it's also going to be 7 centimeters. So we do actually already know that we're going to get pi. It's going to be 1/3. So V is going to equal 1/3 pi times 7 squared times 7. All right, so we already know that that's going to be, in fact, the case. Great. All right, so that's what we're going to be looking for in terms of our end result. Now, what I'm going to do is I'm going to imagine, okay, I'm going to imagine what each one of these cross sections look like. And so each one of the cross sections, their cross sections are going to be circles, okay? And the question is how big is the radius? What does r equal? Well, how I'm going to think about this is I'm going to say, well, okay, the height, let's make this x, this the x-axis. And so here's 0, 0, and this is 7. Okay? And so as I move along the x-axis, I'm moving up the x-axis, what's going to happen is that my height, h, is going to end up equaling 7 minus x. So like when I'm at x equals 1, the height equals 6, right? Because it's going to be 7 minus 1, which equals 6. Or at x equals 5, the height ends up equaling 2. And that's what my radius is going to also equal. So my radius is going to equal 2 there too. My radius will equal 6 right here as well. Okay? So what I'm going to do is I'm going to say, okay, well, if that's the height, there's the height is 7 minus x. Okay? Well, that's also going to end up being the radius. So the area, A, of x here of my cross section is going to equal pi times 7 minus x squared. All right, because this is going to be the radius, because the radius equals the height. So to find my volume, I'm going to take v is going to equal, we're going to go from 0, because that's the last x value that I have, up to 7. So 0 to 7, okay, of pi times 7 minus x squared dx. And that actually finishes out my formula, okay? A of x, my area, dx. We'll use a u substitution, so we'll let u equal 7 minus x, and we'll let du then equal negative dx. So v is going to end up equaling the integral from 0 to 7 of negative pi u squared du, which is equal to negative pi times 1/3 u cubed from 0 to 7. And we're going to then resubstitute, so we'll get negative pi times 1/3 times 7 minus x cubed, evaluated from 0 to 7. And so what this will end up being is it'll end up being negative pi times 1/3, or excuse me, it'll be negative 1/3 pi times 7 minus 7 cubed minus 0 minus 7, or excuse me, 7 minus 0 cubed. And so that'll end up equaling the negative 1/3 times pi times negative 7 cubed, which is 1/3 pi times 7 cubed, which is exactly what we got before. Okay, so the big part here, the big part to understand as we're working through our integration, is that our volume is always going to end up being the integral, okay, evaluated on, in this case, the x-axis from on whatever interval that we're looking at, of the area of whatever the cross section is, dx, or dy if we're doing it with respect to y. Let's take a look at another example.
What if our figures aren't actually as, even as that cone? In this case, let's say, for example, suppose I want to find the volume of the solid generated by y equals x cubed on the interval 0, 0 to 2, 8, revolved around the x-axis. So just like the last one that we did, we want to actually go in, and in this case, we're going to revolve it around something. We're going to revolve our solid of revolution around the x-axis. And so I'm going to imagine what this looks like. And so there's my curve, okay? And we're revolving around the x-axis. We're going to go from here's 0, 0 to 2, 8, okay? And here's 2, 8. And so now I want to imagine here's the solid that gets generated as I revolve it around that axis, right? It kind of looks like the bell of a trumpet. Okay? Now, if I think about this, what I'm going to do, I want to find the area and that, or excuse me, the volume, and that volume is going to equal the integral, right, from x naught to x1, okay, of a of x dx. Now, x naught to x1, we got our first value of x, this is going to be 0, and it'll go from 0 to 2, a of x dx. The challenge for us is going to be able to figure out what exactly that cross-section is, okay, and how it is that I'm going to find its area. Well, if I kind of imagine what it looks like, what it is we call this here a disk, okay? So my cross-section is going to look like a disk. It's a circular figure, okay? And here's my radius. My radius is right there, right? That's the radius of the disk. So I imagine here I've got my radius there, okay? And if I want to know how big is that r, okay, that r is equal to f of x, my function, okay, or y, my y value, right? And it's going to change. It's going to start at 0. It's going to start actually having a radius of 0 at a point, right? That's r equals 0. And then finally, it's going to end up at r equals 8, right? Okay, because that's how big y gets when we get to the end. And in between there, it's going to be all dependent upon y equals x cubed. Okay, so my radius here, r, is equal to x cubed. That's my radius, x cubed. Okay? Now, if I take my volume, so v, or so since that's the case, since r equals x cubed, that means my area, a of x, is going to equal pi x cubed squared. So my integral is going to be the integral from 0 to 2 of pi x to the 6th dx. Okay? And this is kind of tricky. It's a tricky way of thinking, but you just want to see, okay, just like when we were doing the surfaces of revolution, when we're working with volumes, that radius is just simply the value of the function. Okay? So that radius, r, again, equals f of x. We just want to be real clear that that's what it is. All right? Then we go in, we just come in through here and integrate. So we end up with 1/7 pi x to the 7th, integrated from 0 to 2. And so we end up with 1/7 pi times 2 to the 7th. And that, in fact, is our volume, V. Okay? So it's really all about the setup. In fact, oftentimes when I actually give you one of these problems to work on for an exam or something, I may just ask you to do the setup. Okay? Now, just like with surfaces of with surface area, it's going to matter whether or not we're revolving around the y-axis. So let's take a look at the same problem, but now let's think about it with respect to the y-axis. Okay? So what I'm going to do now is I'll draw my figure, and the figure's going to look the same. Okay? So this is respect to y-axis. So there's my figure, and now I've got 0, 0 down here, okay, and I'll go up to 2, 8. And the first thing I want to notice is as I revolve this around the y-axis, I get a different looking figure. I get something that looks more like a bowl and less like a trumpet, okay? In addition to that, my interval changes. So my interval, okay, my y0 to y1 is going to be based upon y, and so it's going to go from 0 to 8. Okay, we go from 0 to 8. And now I want to look at it and ask myself, well, what are the cross sections here? All right, so if I take a look now and look at my cross sections, there's still going to be circles, okay? There's still going to be circles, there'll still be discs. And here's my radius, but my radius is now a function of y. Or excuse me, is a function of y, and it's equal to some value of x, right? Because it's going to be somewhere down here on the x-axis. So what I'm going to need to do is I'm going to need to transform. I've got y equals x cubed. Well, what I'm going to need to do is transform it into x equals the cube root of y, just like we did when we were working with surfaces of surface area. So we turn that into a function of y, and so that's now my radius. So it's the cube root of y. And so my area now, a of x, is, or excuse me, A of y now is going to equal pi times the cube root of y, or the cube root of y squared, which is pi times y to the 2/3. So my volume is then going to be pi y to the 2/3 dy now, because we're revolving around the y-axis. Given that's the case, okay, now it's just a matter of, this is basically using the power rule, we're going to end up with 3/5 pi y to the 5/3 evaluated from 0 to 8. And so this is 3/5 times y, pi times 8 to the 5/3. And then, of course, minus a 0, because 0 to the 5/3 is just a 0. Okay? So let's make sure this is a power. And if you go and check against what we got in the previous question, these are very different numbers. 3/5 pi times 8 to the 5/3 is very, very different than pi times is very different from 1/7 pi times 2 to the 7th. All right, so when you're integrating with respect to y, or the y-axis, what you're going to be doing, just like we did with surface area, is you need to change your function into a function of y. You need to find the intervals on which you are determining with respect to y rather than with respect to x, but then it's the same idea, okay? Right? Now we need to find that radius, the radius of, in this case, the circular region of our disk, okay? Right? And we basically are going to be plugging that into our formula for the volume. Now, when we were dealing with surfaces of revolution, one of the things that we didn't really ever need to deal with is what happens if we have more than one curve, okay? What you kind of want to imagine, what I imagine actually for myself is to think about like one of those Ben and Jerry's ice creams where you've got like the ice cream on the outside, and in the middle it's got a core, and I think they're called cores or something like that. And so you've got the ice cream on the outside, and then you've got this core in the middle, and then the whole idea is to eat the whole thing all at once, right? But you might ask the question, what's the volume of ice cream in there versus the volume of core? So like how much ice cream is actually in there? And so what we need to do is we're going to kind of like work with the same ideas that we were working with when we were looking at the areas between two curves, all right? But what we'll do is that we'll, instead of just taking the integral of the two functions, we're actually going to utilize this whole idea of working with disks, and I'll show you what I mean in just a moment. All right, so let's imagine that I've got two functions. I've got y equals x squared and y equals x. All right, so I've got these two functions, and I want to revolve, I want to find the volume of the surface of revolution generated when I revolve these two curves around the y-axis, or excuse me, around the x-axis, around the x-axis. Now, what I'm going to do, I'm going to kind of imagine, here's my axes, okay, and I've got y equals x, and then I have y equals x squared, okay? And the first thing that I want to notice is I've got, they're going to go from 0, 0 to 1, 1. And you can find that just by setting x squared equal to x, okay? And solving, right? Same idea that we were working with when we were dealing with surfaces of revolution. We actually just set the two equations, the two functions equal to each other, and then figured out what the value for x was in that case. Okay? So this integral is going to go from 0 to 1. All right? And we're revolving around the x-axis, so it's going to kind of look like this. So again, it's going to have this quality. However, it's not going to look like a trumpet. It's actually going to look like a cone with a trumpet cut out of it. Okay, so it's going to be all this stuff in here. Okay, it's all this stuff actually on the outside. right? So it's like kind of thickest in the middle, and then it's really thin on the other sides as the two curves start to intersect each other. So we need to find out uh, what the um, what the areas are for the discs in there. Now I'm going to imagine one that's in the middle rather than one that's in the end, because the ones at the middle are going to be the easiest ones to think about. So I look at this and I got the one at the middle, okay? And on the outside, right? So this big circle, it has a radius of x, right? Because the x is the y equals x is the one on the outside, so its big radius is x. And then the one on the inside, it's got a radius of x squared. Okay, it's got a radius of x squared. So the area of the region, right, okay, that we're looking for, we want to know how big is this region, the region in between the two. How big is that region right there? And so how we figure out that region is that that's going to be pi x squared minus pi x squared squared, right? You're going to take the big circle minus the small circle, right? And that's going to give you the area, right? The area of the interior part. And this is going to equal pi, right, times, and this will be one of those functions, is x squared minus x squared squared. Okay? And so that's going to end up equaling the integral from 0 to 1 of pi times x squared minus x to the fourth, okay, dx. And then you just go in there and you integrate. Figure out what that is as an integral. I'll leave that guy up to you guys. But that's the idea. This thing here, we sometimes will call this a washer, right? Because that's what washers look like. They're, circles with holes cut out of the middle of them. And so this is then called the washer method. And what did we do? Well, all we did was we figured out what the area was of the big circle on the outside, and we subtracted from it the area of the small circle on the inside. And we utilized the methods that we'd been doing for the rest of this lesson in order to generate what those areas actually were and what those radiuses were. So now the question is, what if we want to revolve this? We want to find the volume revolved around the y-axis. Well, it's going to be basically the same process as we had before, okay? But it's going to take a little bit of more thought and a little bit more kind of visualization. So here's y equals x again. Here's y equals x squared, right? We got that parabola. We're still going to go from 0, 0 to 1, 1, because that's still our intersections, okay? So we're going to have the integral from 0 to 1 of a of y now dy, okay? Because we're going to take the integral with respect to y dy, all right? And so I'll have y equals x. So basically, if I rewrote that as a function, x is a function of y, I get x equals y. Same deal. And then y equals x squared then becomes x equals the square root of y. Okay? All right? Now, what I'm going to do is I'm going to imagine, or I'm going to visualize my surface of revolution. And what you're going to notice is that there's a switch. The switch is that the big circle, if I imagine a disk now, my big circle, okay, has a radius of the square root of y. Okay, it's actually going to be the parabola that's on the outside. And my small circle is now going to be the one that has y equals x, or in this case, y. So that x equals y is my small r, call it r2, and my r1 is root y. Okay, so what you're going to notice here when we're working with revolving around the y-axis is that your big circle, your so-called big circle, is going to be the one that is furthest, right? The big one is the one that is furthest right, okay? And the small is going to be the furthest left, or the closest to the y-axis, okay? Because if you can kind of imagine it, this point right there, it's pointing out directly at you. That's the y-axis. Okay? So in this case, what we get is we get pi times the square root of y squared minus y squared, and that's our area. So now, or excuse me, that's the area of the figure. So now we get 0 to 1 pi times, and this will end up being y minus y squared dy. Okay? So unlike with when we shift to revolving around the y-axis, what we need to do is we need to start thinking about the outer function and the inner function. They might switch positions, okay, depending upon what we're looking at. You may also see, by the way, as you do work with these kind of things, you may see where depending upon the figure, right, or what you're being asked about the figure, you might actually have one function be the inner function and the other function be the outer function, and then at some point in time switching places. And then in that case, what you're going to need to do is you're going to need to actually take two integrals and add them together. Okay? But basically, what we're doing here, whenever we're looking for volume, when we use this washer or disk method, is we're going to go in and we are going to find, okay, the area of its cross section over an entire interval. We're going to integrate the area of a cross section over the interval, and then that is actually going to end up giving us the volume of whatever figure that we're looking at. Okay? So we've got two basic functions. All right, so to put everything together, what we want to do is we want to kind of just imagine, well, what are some of like basic formulas that we work with? And then from there, it really is all about visualization. Okay, can you visualize what these figures look like and how to put them together? Because basically, if we're going around the x-axis, so we're working around the x-axis, then our volume is just going to equal the integral from x0 to x1 of the area of a cross-section dx. And if we're working with a surface of revolution, then what that means is either we have a disk, which is a solid disk, and then my volume is going to be equal to the integral of x0 to x1 of pi f of x squared dx, right? So basically, that's circular cross-section, all right? Or if we're working with a washer, then we're going to get v equals the integral from x0 to x1 of pi times and f of x squared minus g of x squared, where f of x is the function furthest from the x-axis. Okay, and so that's basically it, right? Essentially, what we've got here is we've got the subtraction of two circles. We have a circle right here, okay, and we're just actually stacking up those circles along an interval on the x-axis. Now, with regard to the y-axis, what we'll get is we're going to get v is going to equal the integral from y0 to y1 of a of y dy. Okay, so everything gets written as a function of y. Our disk will end up being v equals the integral from y0 to y1 of pi times f of y squared dy. And our washer, okay, and again, our outer function, okay, our washer will be v equals the integral from y0 to y1 of pi times f of y squared minus g of y squared dy, where f of y is the function furthest from the y-axis. And so that kind of completes this idea of this disk and washer method. What we're going to be looking at next is we're going to be looking at this thing called the volume by shells or cylindrical shells, which is a little bit more difficult to imagine or to think about, but kind of plays on a lot of these very similar ideas. All right, so we'll see you then.